Okay, so welcome back, everyone. So our next speaker is İlhan İkeda from Boğaziçi University and Feza Gürsey Center for Physics and Mathematics. And he'll talk on the Langlands reciprocity and functoriality principles.
Thank you very much, Alp. In fact, I should thank Hadi, Ismail, and Ali for having this idea for a joint meeting between Feza Gürsey Center, the old name is Feza Gürsey Institute, and IPM. So this is the first joint meeting. I hope we will going to have more in future. So the title of my talk is on the Langlands reciprocity and functoriality principles. In fact, I have talked on this issue, at least certain portions of it before, so some of the audience may know some parts of it. But anyway, so let me start. Oops, why? Oops. Why it doesn't go? Yeah, I'm sorry, yeah. So the outline of the talk goes like this. The first part, restricted free products of topological groups, is purely a universal algebraic part of the discussion. Then I will apply this theory in relation with automorphic Langlands group, Lk, of a number field K. This is a purely conjectural group for the time being. And then I will apply the results that I, saying results is kind of too much. The observations that I will make in the second part to the last part on the reciprocity and functoriality. So let's start then. So the notation that I will fix in the first part is we have a collection of topological groups. They are indexed over some countable set I. So these topological groups are supposed to satisfy a certain technical condition that I realize that one has to impose such condition quite recently, actually. But I will not give the definition of K omega topological group, what they are, but it's a certain technical condition on topological groups. But meanwhile, in my talk, I will make it precise why we have to put such an assumption. And for all but finitely many indexing set elements, small I, we fix O sub I, fixed open subgroup of GI. And I sub infinity is a finite subset, is the finite subset of our index set, for which OI is not defined. So the main references here, I list here in this, one of the audiences, I believe he is a graduate student, asked for references. So these are the main references. So anyway, I will put slides somewhere and one can look for the references. So first of all, if we have collection of topological groups, then we can define its free product. So star GI, that's how we define. And free product of topological groups exists. And what are the important aspects of free product is that we have canonical embeddings GI sub 0 into the free product star GI for each E sub 0. And also we have the universal mapping property of free product. So what this says is that if you have any topological group H, and for each index element I sub 0, we have a continuous homomorphism from GI sub 0 to H, then we have a unique continuous homomorphism from star GI, the free product of GIs, to H. So that, I'm sorry, when I compose with I sub zeros, these canonical embeddings with phi, I end up having phi i's. So this is the universal mapping property of free products. So how I define my algebraic object, let me say, this is called restricted free product of topological groups. So first of all, in my indexing set, I specify finite subsets S, but with the condition that I infinity is contained in S, and I introduce the topological group G sub S as the free product of O sub I whenever I does not lie in S, and free product of GI when I is in S. So this is my, I take this free product and I denote this by G sub S. So if I have two such finite subsets S and T containing I infinity, then I can uniquely define a, I'm sorry. Oops, I'm sorry. Yeah, I can uniquely define a continuous homomorphism tau from GS to GT in case S is inside T by the universal mapping property of free products. Okay. So how I define the restricted free product of the collection GI with respect to the collection O sub I? That I denote by star prime GI index OI, but I may just call it star prime GI to simplify the notation. This is defined as the injective limit, direct limit of the collection GS that I introduced in the previous slide, where the connecting morphisms are these taus from GS to GT. And then the topology on star prime GI is defined by declaring X to be open if X intersection GS is open in GS for every S. So endowed with this topology, star prime GI is a topological group, and you see, if we don't assume that that I is countable and GIs are K omega topological spaces, this, okay, we can still construct such a direct limit and we end up having a group, but this is no longer a topological group. It turns out like that. In fact, when I realized that this is not, this may not be a topological group, I said that this construction probably will fail. But then, when I was looking at some references and so on, it turned out that there is this concept called K omega group, and which behaves well with respect to taking direct limits of collection of K omega groups and so on. So then I decided to impose this extra condition. Moreover, it turns out that the groups that I will be interested in, I will later on specify GS to some certain number theoretic objects, certain number theoretic groups, then all of these topological groups turn out to be K omega. So then we are fine, at least, yeah. So, okay. Moreover, we defined restricted free product of the collection of GI. They have similar universal mapping property. So what it means is that if I have H a topological group and phi I GI to H continuous homomorphism, then there exists a unique continuous homomorphism phi from star prime GI from the restricted free product to H, which satisfies, so these CSs, they are the canonical maps of the direct limit. So when I compose with these CSs with this phi, I end up having phi of S. Phi of S is, this is, you remember, these are free products. This phi S is the free, the homomorphism obtained by the universal mapping property of phi i's. So that's how we have a group, a topological group, and it has a nice universal mapping property. So we have some basic facts. For example, how is that? I have this script G to denote the restricted free product of GIs. Then if I denote by script I0 to be GI0, then there exists a natural homomorphism from GI0 to G. It is defined like this triangle, commutative triangle. It seems at first to be defined on the finite subset S, choice of S, where S is a finite set containing I infinity. But it turns out that you can change, you can consider any finite set containing I infinity. This map is the same. It turns out that it's independent of choice of S. Also, I mean, if I have phi prime from G, this is my restricted free product to H is a topological group, a continuous homomorphism. So when I compose with this Qi0 that I defined, which is independent of the choice of S, if I compose with, I end up having phi I naught. That's another interesting, nice property. These are very easy to show. And if G and H are two topological groups, so we say that what H conjugacy means that, and Xi is a topological group homomorphism from G to H, and Xi prime is another topological group homomorphism from G to H. We say that they are H conjugate if they differ by an inner automorphism, iota H, like this. So, and I define this script G is my restricted free product. If I have a continuous homomorphism from my restricted free product G to H, and phi prime is another continuous homomorphism from my restricted free product G to H, we say that they are locally H conjugate. Phi prime and phi are locally H conjugate. If in the, well, this phi is, when I compose with Qi0, I end up having phi I0. When I compose this with Qi0, I end up having phi I0, right? So phi prime I0 and phi I0, they are related like this. If they are H conjugate, if they are H conjugate, I will going to say that these phi and phi prime are locally H conjugate. Oops, I'm sorry, what happened? Okay. So to H conjugate.
Sorry.
Yes. Yes.
Do you want to generalize the notion of A-design ideals to more general setting?
Well, thank you very much. Yeah, exactly. In fact, that's what I am. That's what is in my mind. So I am coming to that point. So one more property. Thank you very much. If phi and phi prime are locally H conjugate, then kernels are the same. That's one. Okay. So now, why restricted free products? Why I am interested in restricted free products? The reason is the following. If I have my restricted free product and if I abelianize it, it turns out that it is the restricted direct product of the abelianization of GI and with respect to the abelianization of OI. So probably this is one hint why I am interested in such structures. That this is these structures, they are like non-abelian analog of, or non-commutative analog of ideal group, as you pointed out. So, by the way, the proof of this seems easy, but it was not actually. I mean, anyway. So, not only that. So suppose that now I will choose my index set I as the set of places of a global field K, and I sub infinity as finite set consisting of all infinite places of K, and GI for as I runs over my indexing set, and OI as certain topological groups defined in terms of the global field K, in such a way that if I abelianize GI, I end up having Ki star. I'm sorry, what Ki star? Ki star. Yeah, Ki star. Because I is the set of places for all places of K, and OI abelianization is the UKI, the unit group. Then, when I abelianize under this setting, I end up having the ideal group, right? So this can be viewed, provided that if I can find such GIs, then this abstract group, abstract topological group, let me say, can be viewed as a non-commutative generalization of the ideal group. So this means that we need an abelian we have an abelian generalization of the ideal group, J of K, that I denote like this, of K, is only possible if we have a reasonable local non-abelian class field theory of K, but in the sense of Hasse, for finite places of K, not in the sense of Langlands for the time being, in the sense of Hasse. So, I mean, what this means, I will explain it now. So this completes the chapter 1 of my talk. This is chapter 2. So here we fix a number field K and the set of finite places of K denoted by HK or FK, and infinite places of K denoted by AK or infinite K, and K sub nu, the completion of K at place nu. So these are the main references that I use in this chapter. So let's start with it. So remember that what I told you is that we need to develop Hasse-type non-abelian class field theory. In fact, it turns out that there is such a theory. First, it was initiated by Helmut Koch. He developed it for meta-abelian. So you have a local field K, and you consider a non-abelian extension, Galois extension, whose second commutator subgroup is trivial. So such extensions, they are called meta-abelian extensions. So in case we have meta-abelian extensions, Koch developed a class field theory in the sense of Hasse. Later on, Fesenko considered, instead of considering meta-abelian extensions, he considered something, a type of extension introduced by Fontaine and Vintemberger. It's called APF extension, where APF extension and field of norms construction, they are kind of the primitive form of Scholz's perfectoid theory. Anyway, so Fesenko did the same for APF extensions. And what I and one of my PhD students, we developed is that we developed for whole absolute to KSEP. We managed to move to KSEP. Why? Because we realized that one can cover K to KSEP with APF extensions. So it was kind of taking a nice projective limit, defining such kind, but it is a non-trivial work. One has to be careful. There are technical computations, but anyway, so there is indeed a certain topological group we denote by nabla K, which depends on K nu, but this has a one drawback. We have to fix a lifting of the Frobenius automorphism of KNR to KSEP. We have to fix one extension. That's it. But if we change the extension, then the topological groups nabla are related somehow via conjugation. So it is not a big deal. There exists a topological group which depends on K nu, which is isomorphic to the absolute Galois group. Moreover, this isomorphism satisfies properties similar to class field theory, like, how shall I say, norm functoriality with respect to norm, and well, we have existence theorem and so on. I mean, so in that sense, this map deserves the name non-abelian norm residue isomorphism, or Artin isomorphism. So I call this in Galois form. Why? I will explain later on. So there is also the Weil form. Instead of considering GK nu, I am going to consider the absolute Weil group of the local field. Then it turns out that there exists a certain, so algebraically these are subgroups, they are dense subgroup, but topology is a bit different. But anyway, we have a certain group, Z nabla set, preserving this isomorphism. So this is the Weil form of this Hasse type local non-abelian norm residue symbol. Yeah. So moreover, it has a ramification theory. So ramification filtration on the Weil group side, and there exists a filtration which is like when you abelianize, you end up having the higher unit groups here. You have a compatibility with respect to this isomorphism. So to sum up, we have the following chart. So this is the theory that we developed. So we have to fix phi of K. And when you abelianize, GK nu goes to GK nu up, nabla goes to the profinite completion of K nu star. Weil group, absolute Weil group goes to the abelianization. And when you abelianize Z nabla, it goes to K nu star. And also inertia goes to abelianization of inertia. And this subgroup goes to the unit group. And higher unit groups behaves like, higher ramification behaves like this.
Can I ask a question?
Yes, of course.
So you're saying that the abelianization of nabla is these fields below, these subgroups of K star?
Right.
Okay, thank you.
So this is the chart, more or less we have. Now, we have also in Langlands program, the absolute Langlands group of the local.
Excuse me, can I ask another question before you continue?
Yes.
So
yes.
The construction of these nablas,
Yes.
you have to start with a global field, or can you define them for a local field as well?
This is totally local for local field. I just choose global field before because I will go to the idyllic techniques because of that. But K can be any local field, you just do it. Characteristic 0 or characteristic P, it doesn't matter.
Okay, thank you.
So now, how the absolute Langlands group LK nu is defined? It is, you take the Weil group, local Weil group, and you take SU2, you take the direct product of it. This is the local Langlands group. So we have also the for Archimedean primes, we have Weil group as well. Now, so very naively, how I define, there is the Langlands form of local non-abelian norm residue isomorphism as, so LK nu is WK nu times SU2. So I will consider the Langlands form of non-abelian norm residue symbol as the Weil form times identity of SU2R. So it is this. So I mean, I choose this identity SU2R. This may cause problem maybe in the theory in future, I don't know. But for the time being, very naively, I choose like this. Okay. So this means that for non-abelian norm residue isomorphism, I have Galois type, Weil type, and Langlands type. I have 3 types. So how I define Weil-Arthur ideal group of K? So first of all, I should mention that this is an unconditional non-commutative topological group. It doesn't depend on any conjectures. So for GI, I choose, how do I go up? Wait a second. No. Okay. So for GI, I choose these topological groups. And for OI, I choose the one corresponding to inertia times SU2R, and I keep the Weil groups the same. So this is my restricted free product, WA. So R1 and R2 corresponds to the number of real and complex Archimedean primes. So this is non-commutative generalization of the ideal group of K. So when I abelianize, I end up having, obviously, I end up having the ideal group. Okay. Not only, so what is, it is, so what I'm claiming is the following. I claim that this WAK, this topological group, is related with the automorphic Langlands group. Why is that so? Here now I will apply my universal mapping property. So how? So we already know that we have, okay. So for the time being, let us assume that automorphic Langlands group exists, let's say, for now, okay? So then one of the formal properties of the properties that we expect it to satisfy is that if I choose and fix an embedding from K sep to K nu sep, then up to LK conjugacy, we should have an embedding or a map from LK nu to LK. That I denote as E nu Langlands. So now, if I compose E nu Langlands, which is a map from LK nu to LK, with my reciprocity isomorphism, this one, non-abelian norm residue isomorphism of K nu in Langlands form, this, then I end up having an arrow from this topological group to LK, unique up to LK conjugation. So by the universal mapping property of restricted free products, we end up having the following result, right? I have this collection of arrows, and this collection of arrows should define a map from where Arthur ideal group to LK, right? And this is unique up to local LK conjugation. That's the reason why I made such a definition before. So this arrow very much behaves like global abelian norm residue map of K that I tried to work out very meticulously in one recent work of mine. And moreover, this result is compatible with Arthur's construction of LK, namely, instead of considering LK, if I replace LK with Arthur's LK, let me say, then still I have a nice map that goes on like this. So my conjecture is that this homomorphism is open and surjective. This is my conjecture. I strongly believe in that, but of course. So now, this is chapter, I have 10 minutes, I guess. How many minutes I have?
Yes, around 10.
Okay,
bit more.
So, yeah. So here, this NR Langlands was the map, this one. So I denote kernel of this with this script N. So G denotes a connected reductive group over K, and G nu is G viewed as a group over K nu, and we have the L group of G and G nu, and we have also embedding of LG nu to LG. These are the ones that we fix. The references that I use are these ones, so one can look at that, especially these two. This one, Arthur's paper, is very influential. So I introduce new type of parameters of reductive group. So how is that? So here we recall the definition of morphisms over a group. So H, M, two groups, endowed with projections or group homomorphisms H to W, M to W. So if such thing becomes commutative, F is called a homomorphism over W. So semi-simple elements in LG, we have elements in LG can be considered as pairs like this, and it's called semi-simple if Rx is semi-simple in GLNC for any n-dimensional representation. So we have semi-simple homomorphism definition here. So maybe I go to the definition of
İlhan, sorry, I made a mistake with the calculation of the time. I'm very sorry about this. You have a bit more time until a quarter past. In fact, you have still 25 minutes.
Oh, okay, I see. Excellent.
Yeah.
So, okay. So we have, so an n-dimensional representation R of LG over C, we mean a continuous homomorphism to GL and C, such that when we restrict to the dual group, it's a homomorphism of complex Lie groups. These are definitions that one can find in Borel's Corvallis lectures. And semi-simple homomorphism H to LG, HC group, is a group homomorphism. It's called semi-simple if FH is semi-simple for every element. Okay.
Sorry, can I ask a question?
Yes.
I didn't quite follow. So G is, let's say, a connected reductive algebraic group or a semi-simple algebraic group? Because I'm not sure why you're writing G of C and then L group. So you just mean that it's a complex group and then
yes,
you
exactly.
make the
Yeah.
Okay.
Because you see many people write LG, right? But I have recently seen some papers, especially written by what was Kevin Buzzard, maybe. He considers LG of QL and so on, QL rational points. So because of that,
so he takes for the dual group like the QL points. Is that what you're saying?
I guess so. I mean, he considers map from wave group to LG of QL bar and so on.
Okay.
So in that sense, I mean, so
okay.
probably.
Okay. But your G is also a reductive, like a connected reductive algebra.
Yes. Okay. So I mean, in the classical standard notation, it's LG.
Yeah.
It's LG. Yeah. Okay. So H is a group homomorphism called semi-simple if FH is semi-simple for every H in H. So definition of equivalent homomorphism goes like this. Group homomorphisms F1, F2 are equivalent if we can find an element G in the dual group so that F2 is G conjugation of F1. Right. So these are equivalence relations, equivalence classes. I will denote by bracket. And equivalence relations preserve semi-simplicity and continuity as well. Yeah, these are the remarks that we have. So from now on, G is assumed to be, as in most literature assumed, it is quasi-split. Well, I mean, some people drop quasi-split assumption recently, I think Caleta and so on. But anyway, so ordinary quasi-split group. And L homomorphism is H a topological group with a continuous homomorphism PH H to WK. A semi-simple and continuous homomorphism over WK is called an L homomorphism from H to LGC. That's a definition of L homomorphism. And global L parameters of G over K are semi-simple and continuous group homomorphisms phi from LK. This is our automorphic Langlands group to LGC over WK. And this its equivalence class bracket phi that we introduced here. Global L parameter of G over K. This is how global L parameters of G over K are defined. So now we have standard notation phi tilde KG, the set of L homomorphisms from LK to LGC, and phi K, the set of all global L parameters. So these are the equivalence classes of L homomorphisms. These are L parameters of G over K.
Sorry, can I interrupt again?
Yes.
So this global LK that you write is very much conjectural, right?
Yes, exactly.
Okay, so I just wanted to, so you're not suggesting that you already have sort of a construction of that?
Well,
I know that's what you're working towards, so I was just wondering how far you are.
Yeah. I mean, so let me put it like this. This is LK here is the conjectural LK, let me say like this, as you said. But I mean, my impression is that one can construct this LK somehow. I mean, but still, I mean, one has to do some work, but I mean, that's my hope, I mean. So we have the local counterpart as well. The local L parameters, they are exactly defined in the same way, where phi tilde K nu G nu, the set of all L homomorphisms from L K nu. L K nu here this time, it is not conjectural, it is a concrete group to L G nu, and by phi K nu G nu, the local L parameters, the bracket of them. So Well, I mean, there is G relevancy thing, but I will not, I haven't written anything on that. But anyway, so one can drop the assumption of quasi-splitness and so on, but okay, very good. So now, instead of L parameter, I will introduce something called WA parameter, and it is like this. Instead of considering LK or Weil group of K, let us consider WA of K. First, we recall that this is an unconditional group. So this group exists concretely. So one can consider continuous group homomorphism. This is a topological group because in the beginning of the talk, I said that in the ingredients, one has to consider K omega groups. And it turns out that one can show that Weil groups and SU2 and so on, such groups turn out to be K omega group. So this is a topological group. So we can consider continuous group homomorphism from this ideal group, WA ideal group, let me say, to LG over K, over WK, over the Weil group, global Weil group. So there exists a natural map from Weil-Arthur ideal group to global Weil group because one can define a map from Weil-Arthur group to the restricted free product defined by forgetting SU2s, and it has a natural map to WK using the universal mapping property. So its equivalence class we denote by bracket phi. These consist of G hat conjugates of phi. WA parameter of G over K is this object, so bracket phi. So I put WA on top of this to denote WA parameters. So what are the basic properties? The basic property is that so LK nu is mapped to this group. So I can make this composition. So if I have an L homomorphism from W A to LGC, then for every finite place nu, this composition factors as, wait a second, like this. So LK nu to LG nu, yeah. Therefore, there exists a mapping from WA parameters of G to the product of local L parameters as nu runs over all places. So we have such, so if I have an L parameter, if I have a WA parameter, then I can write down a collection of local L parameters. And it is defined like this. Phi is mapped to phi nu bullet. It is this one. Okay. Very good. Moreover, one can show that this map from WA parameters of G to the product of all phi tildes, this is an injection. Therefore, we have such, I'm sorry, I forget to add. Moreover, being equivalent reflects on going to the local components. So phi is equivalent to psi. The parameter WA parameter phi is equivalent to WA parameter psi. Then the local L parameter phi nu bullet is equal to the local L parameter phi nu bullet. That one can show. So we have such a mapping in the WA parameter level. So this is for, so passing to equivalence classes is well behaved. That's what I'm saying. So equivalence class of phi goes to the equivalence class of local L parameters.
Is this still injective?
It is still injective. Yeah, this is injective. Yeah.
Okay. Thank you.
So the first result is, in fact, that's an injection. Very good. So we have an embedding of WA parameters to the product of local L parameters of J nu as nu runs over all places. So actually it is possible to make it a bijection also, but then we have to extend the definition of WA parameter a bit. So this is the first result. Now we can apply this result to global reciprocity principle for G over K. Actually, for the time being, global reciprocity principle for G over K, well, one of the ingredient is missing, and it is L of K, the absolute Langlands group of K. So either people talk about considering representations of the Weil group or representations of the Galois group, or one assumes LK and talk conjecturally. And that's what I'm more or less doing. So let pi k nu denote the set of all equivalence classes of irreducible admissible representations of G nu. So the local Langlands reciprocity claims that pi k nu has a partitioning into smaller, how shall I say it, pockets, L pockets, finite disjoint L pockets, where it is parameterized by or indexed by, how shall I say, by this is by L parameters. Yeah, by L parameters. Right. It is like this. So how it is? It is we have such a map. What was lambda? Suddenly there is lambda appearing in such a way that the set of local L packets. Yeah, the set of local L packets. It's defined like this. So we have such a decomposition, and it should satisfy certain naturality properties between between the corresponding things. So if I choose an L packet, an L homomorphism, L parameter, I'm sorry, and it corresponds to L packet, then the corresponding local L factors should match. That's one of the properties. And now I will assume that from now on, local Langlands reciprocity for over K nu should hold for every place. That's my assumption. So I assume that this conjecture, the local Langlands reciprocity, should hold true. Well, recent work of Farg and Scholze on Farg-Fontaine curves and so on and so forth, many people believe that very soon we will going to have local Langlands reciprocity principle, hopefully, yeah. So that's my assumption. I assume that this holds true. So we have Flat's decomposition theorem, which says that if G is a connected reductive group over K and pi is an irreducible admissible representation, then pi is the restricted tensor product of pi nus. Here, pi nus are irreducible admissible representations of G nu, and all but finitely many pi nu are unramified. Therefore, if I choose any WA parameter phi, then our theorem A implies that there exists a collection of phi nu bullets, and these phi nu bullets are local L parameters, and by the local Langlands reciprocity principle, these local L parameters correspond to L packets corresponding to local L packets corresponding to phi nu. Very good. Therefore, this Flat's theorem states that if we have this, how shall I put, this pi, so this is isomorphic to this restricted tensor product, then it is associated with the WA parameter phi, right, via this. So how we can say is that global Langlands reciprocity principle for G over K, assume that the local Langlands reciprocity principle for G nu over K nu holds, and for all connected group G equals split reductive group G over K, then what we have shown is that there exists a bijection from WA parameters with the collection of all, these are the admissible representations, I think. Where was it? Oh, I'm sorry. With L packets of G, WA parameters to admissible L packets.
So you have it actually right on this page, just below Flat's theorem. You say it's the global admissible L packet.
Yeah. That's true. Yeah. So moreover, if we assume the existence of LK, so up to here for this one, I do not assume. How shall I put it? LK. So up the moral of the story is that, okay, what Langlands claims is that LK is the universal group for automorphic representations. But what I am saying is that, okay, instead of LK, I have a concrete group which is in bijection. The WA, the parameters with respect to that concrete group WA gives a correspondence with admissible L packets. So it is a bit in the higher level. So automorphic representations are inside. So for this cannot detect whether something is automorphic or not. It is just a correspondence between a WA parameter and admissible L packets for the time being. But now, how it goes on, I'm sorry, let's continue. So suppose that we assume the existence of LK. Then, and the conjecture that we introduced above, so the conjecture was stating the following: WA ideals maps surjectively to LK. So what this means is that LK is a quotient of WA. Therefore, phi is an automorphic L packet if and only if phi, this WA L packet, WA parameter, I'm sorry, WA parameter or contain the kernel of WA parameter contains the norm of this map that I introduced. This is a criterion, actually a congruence relation or imposed on admissible representations, whether it is automorphic or not, but provided that LK exists. Okay, so that's one of the things. Now, regarding functoriality, having said this global reciprocity principle, one can say similar things for functoriality. So G, I have a rho, an L homomorphism from LG to LH, then composing with here with WA, where are two ideals, I will going to obtain an, how shall I say, a map from WA parameter of G to WA parameter of H. And then combining with this bijection, I will going to have a map from lambda kg to lambda kh. But still, there is no condition on being automorphic or not, just on the admissibility level. Because the problem is we don't know, first, for the time being, we don't know what LK is. That's one thing. And the second thing is that, yeah, but I mean, yeah. But again, assuming the existence of LK and the conjecture that we introduced that WA surjects to LK, then one can say a bit, say things about automorphicity. So pi is an automorphic if rho star pi is automorphic in case because of how shall I say, because when I compose these, if it's automorphic, then it means that kernel should be included. This N should be included in the kernel because of that. Yeah.
So this rho star that you have is actually taking admissible representations to admissible representations.
Exactly.
So it's not about taking packets to packets, right? It's an individual representation.
Well, actually, it is possible.
You even have the notion of packets for admissible representations that are not maybe automorphic?
Well, I mean, one can write it, I believe, right? I mean,
do you have the notion of L functions, for example?
Well, formally, one can write without convergence, right?
Yeah, well, I guess, yeah, okay.
So,
for example, if you wrote it formally, I suppose we don't maybe necessarily have things like functional equation, but I guess if your real part is big enough, you do have at least convergence.
Yeah, convergence when a real part is big enough, but apart from that, I think we don't have much. But I mean, still, I mean, what I'm advocating is in the level of admissibility, admissible level, these concepts fit together. But not only that, actually, this is, of course, I wrote a dream because why is that? Now you ask the following question, whether you want to construct LK. And the answer is yes, actually, it may be possible to make an unconditional construction of LK. So how it is? It should go like this, but I mean, there are some problems. I mean, I don't know. I mean, so it is like this. Okay, there is a correspondence between WA parameters and admissible representations, right? So this means that among admissible representations, there are automorphic ones. So I will pick the automorphic ones and the WA parameter corresponding to that automorphic representation and look at its kernel. And I will take the intersection of all the kernels and then take the quotient with my WA. This huge intersection. Then it acts universally, of course. But I mean, there are many problems. I mean, like if I take this huge intersection, it may be trivial, I mean. So, I mean, this is just a dream for the time being. But one nice and beautiful thing, I believe, is that, you see, I was talking with one Russian number theorist, Parshin, Alexei Parshin, and he said to me that it was very interesting. For him, class field theory should be, even in the non-abelian setting, there should be existence theorem. But I mean, what is the existence theorem in Langlands program? So I said, well, I mean, I don't know. I mean, but I mean, if this machinery kind of works well, then one can write some sort of an existence theorem, but in the following sense. For example, certain subgroups, normal subgroups of WA, this ideal group of non-commutative ideal group of A, of K, should correspond to certain type of automorphic representations in that sense. Like, I don't know, tempered ones or whatever, you know, such things. I mean, maybe existence theorem may look like that. So these are the one-dimensional, and then finally, developing higher dimensional in the higher dimensional setting seems possible. In fact, with one of my former students, we are working on non-abelian local Kato-Parshin CFT and trying to develop restricted free product of Persian Beilinson adels and so on. And thank you for your attention. Yeah.
Thank you.
Is it possible to extend to arbitrary reductive group? I mean, not quasi-split group, because anyway, you can take an extension so that you can make the group as quasi-split. So is there a hope for the extension to arbitrary reductive group?
Well, I think
because over an extension you can make it.
No. I think there is this person named what was that? David Vaughan and Tasho Kaleta. I guess they are working on writing down this theory in the general reductive group setting. But I have to rewrite everything in that setting, I mean, to answer your question properly. Okay, I mean, take pencil and paper and rewrite everything from the beginning. But it should be doable, I believe. I mean, it should be possible, but I mean, one has to work a bit, I believe.
Okay.
Any other questions? Yes, Hadi.
Okay, so can you give us maybe a feeling of this Ray Arthur ideal group? For example, for some, I mean, examples like when cases like if you make extension.
No. You see, I mean, even the local, so you see the local components are basically more or less, they are the absolute Galois group of local field or absolute Weyl group. So, I mean, it is very difficult to give a feeling.
So have you done some computer? I mean, as I said, the cyclotomic extensions, can one write? So you are saying that these are like the absolute Gala group, more or less, the local.
Well, yeah, it is. Yeah, it is WK. You consider all of it. I mean, you don't consider relative parts.
Mm-hmm. Okay.
So, I mean, well,
so I guess if Hadi is asking about the local, I guess what you call Arthur group, I mean, it's easy to say what it is, but I mean, I guess having a feeling for it is a different issue. But it's simply you take the weight group, and then you, I mean, there's different versions of it, but one version would be you take the weight group, and then you multiply it by one copy of SL2C that people usually refer to as the Dolin SL2.
Yes.
And then you actually multiply it by another copy of SL2C that people call the Arthur SL2. So then that's the local version.
I mean,
and then you take the restricted product.
Well, I mean,
these are local, so it's just product of three groups. That's it.
It's the local. I mean, the local terms. But
that's the local. I guess he called it LKV or something. Yeah, that's it. But then what that is good for or how that comes about, I guess, is a different issue.
Well, I mean,
but just the definition itself is just that.
This WA ideal group that I think it is like this. It is a huge chunk of rock. Well, inside this rock, there is this picture. You see, there is this monument, this beautiful art, but it is up to the artist to take this out from this chunk. So WA of ideal group is more or less like this square, but inside hidden it is this. So I mean, it is kind of you have to take lots of congruence relations and take lots of quotients to get a nice result, probably.
Okay. Thank you.
So your example of this picture kind of reminded me of a description that Langlands once gave of his so-called Langlands program. I was a student, I think, at the time, and some of you might have been to that conference where he actually sort of presented the Langlands program as this big elephant.
Right,
and everybody's just understanding one piece of it, and people may not know that it's actually an elephant, but somebody is like, looking at the trunk, somebody is looking at the head or the tail.
Yeah, exactly. In fact, actually, there is one book by actually a category theorist, but it is on topos theory. Algebraic geometers, I am sure they know. Sketches of an Elephant, the name of the book. It is like thick topos theory books, like thousands pages thick, I mean. Well, okay, so thank you for your attention and thank you very much. Yeah.
Okay, thank you again. So then we'll continue in 5 minutes with the next talk.
Actually, can I maybe ask to have a 10 minutes break because we didn't have any break between the last two sessions? Would it be possible?
Sure. I think it makes very much sense. So let's continue in 10 minutes then.
Perfect. Thank you. Thank you very much.
So whoever is recording probably